and the slideshow up from current slide. I was trying to think if there are any major announcements. I'm sure there are some. For instance, I know Miss Lawson State coronation is coming up Thursday, I believe it is. There is a faculty and staff meeting this afternoon, I think at 3 o'clock over on the Birmingham campus. I'm not going to be able to go because I've got a mini-term class that starts at 3:15, so I won't be able to make that one. So check with, if you have a 3 o'clock class, check with your instructor to see if what's going on with that, because they may, I don't know if they'll, usually they don't have us cancel classes, but check with your instructor. Now, this is not coming up real soon, but it is coming up that Karen will come in, but there it is, okay. And Richard is here. And Karen's here. Okay. Now, 2 weeks from today, not next Tuesday, but 2 weeks from today, right now I'm scheduled for a doctor's appointment. Hematologist only sees patients on Tuesday morning, so I can't avoid this one. Good morning. Sorry, all right. Okay. Just got to find you now. There you are. All right. Well, something said I didn't hear. Okay. So, unless they change the appointment, which they sometimes do, this has been on the books now for about 4 or 5 months, something like that. So, I don't know, you could have a meeting to go to or something like this. So, but unless otherwise known, I'll probably miss that. The appointment's for 9 o'clock, but I have to be there for blood work at 8 o'clock. So, no way I'll be here for that class if they don't change the appointment. So, I'll let you know as we get closer. But that's 2 weeks from today, not next Tuesday, but the following Tuesday. Okay. There are probably some others, I can't think of them now. Oh, if any of you are interested in that, NASA's Community College Aerospace Scholars Program, the deadline for that application to be in is tomorrow. So you need to get on to that today if you're interested in participating. I have a student, I think a couple of students in some of my classes that have participated, and they speak incredibly highly of the program. It's a lot of fun. There's some travel that they pay for and that kind of stuff, and they just, the ones who I've talked with said they just enjoyed it immensely. Learned a lot. Okay. So that's coming up then. All right. Any questions for anything we've covered so far? All right. We're not on example 2. We're in chapter 2, polynomial and rational functions. We're on the polynomial part now. 2.1 is quadratic functions and models. Okay. And we're not on example 2. We finished example 2, but we're on example 4. They don't have the example 4 on the slide set, so we're using the white space here. So, example 4, bottom of page 118, writing a quadratic function. Now, up till now, they have given you the quadratic function and told you to graph it. Okay? Now they're describing the quadratic function and having you write what that function is. So it says write the standard form. Y'all remember the standard form, right? Okay. It's not quite the same as a quadratic equation, but the standard form for a quadratic function whose graph is a parabola. Hey, guess what? If it's a quadratic, it's going to be a parabola. I got you. Okay. In fact, I think I got all 3 of you. Okay. Ty is here. No, sorry. Remind me? Ty. Okay, you're just sitting back there today. Okay. Oh, you don't have a chair. Okay. All right. Sharona is here. Make sure I find the right spot here. I think that's it. And Aman, right? Okay. All right. Anyone else come in since I called roll? All right. So we're on example 4, page 118, bottom of the page, write the standard form for a quadratic function whose graph is a parabola. Hey, that's redundant, isn't it? If it's a quadratic function, the graph is going to be a parabola, okay? Whose graph is a parabola with a vertex, so they tell us the vertex, 1, 2, and passes through the point 3, negative 6. Okay? So, you tell me what the standard form of a quadratic function will look like. What you want to name it? What's everybody's favorite name for a function? F of x. Okay, let's go with f of x. You don't have to name it that. You could pick anything you wanted to. Now, what does the standard form for a quadratic function look like? Where do you begin? A, parentheses, x minus what? H squared plus k. That's the standard form for a quadratic function. Now, the f of x and x are variables. F of x, of course, is y, okay, and x is x, okay? The others are numbers, okay? Now, the a we'll get to a little bit later, but what in the world is the h in this? Anyone recall? Say again? Which part? The first part, yes, the 3. So this will be a times, so you can fill in 2/3 of the equation right now. X, you tell me, minus 3. Say again? I'm sorry.
It's minus 1, the vertex is 1, 2.
Oh, I'm sorry, you're right. I'm sorry, I'm looking at the wrong point. Okay, you're absolutely right. Minus 1, duh, must be a Tuesday. Okay, minus 1 squared plus 2. Vertex is 1, 2. Good. All right. We got 2/3 of the function done. We're just missing the a. But we haven't used this point here, have we? And what does this stand for? Second? What's a 3? An x value, and minus 6 is a y value. And you just told me what those things were, didn't you? What represents the x? X, right? A times, and that's a 3 minus 1 squared plus 2 is equal to negative 6. That's your y. Okay, we can plug those in here for the x and the y, f of x being y, and then calculate what a is. Then we'll come back and get it back in standard form. So let's do what they tell us to. Minus 6 is equal to a, and what's 3 minus 1? 2 squared plus 2. Now what do we do next? Is equal to, what is 2 squared? 4. So let's put the 4 in front of the a, okay? 4a plus 2. Right? That's a pretty ugly 4. Oh, that's not what I want. Okay. Yuck. So the eraser isn't picking up. Okay. 4a plus 2. Now, what do we do next? Subtract 2 from both sides. I'm going to bring it up here. Minus 6 is equal to 4a plus 2. So we're going to subtract 2 from both sides, and that gives us negative 8 is equal to 4a, because that adds a 0. And then what? Divide by 4, and that gives us negative 2 is equal to a. All right. And here's Charles, huh? Amari, got it. Just got to find you now. you are. Good deal. Has anyone else come in since I called roll? Okay. All right. So let's go back to our function. Here it is. And let's fill in what we know now. Alpha of x, that's your variable, is equal to, what's your a? Negative 2 times x minus 1 squared plus 2. Now, do you have to do anything else? No. It said get it in standard form. That's standard form. Easy part is plugging in the vertex, if you can find the vertex, okay? And then the next part is using this point to calculate the A so you can fill that in. Now we get around to saying, what in the world does the A tell us? It tells us two things here. Anyone hazard a guess? It's what? I can't hear. Okay, let me, yep. Janae, right? Yes. Okay, just trying to find you in the alphabet. Okay. All right, now say again what A tells us. Two things.
It goes up or down.
Okay, and what does this one do? Say again? Opening downward, because it's a negative. So that's one thing A tells us. What's the other thing? Vertical stretch, because it's greater than 1. I mean, the absolute value is greater than 1. So we got a good idea what it looks like, and they show you in the book what it is. We won't get that because they're not doing this one. So let's draw the graph. Now I'm going to draw on top of a lot of this stuff. In fact, maybe I'll erase a lot of this stuff so I can draw better. All right, for me to erase a bunch. Okay. Okay. All right, that's all I'll leave here. Well, there it comes. Okay, so let's do our axes here, and somewhere probably, let's just let that line right there be our horizontal axis. So we'll tick off a few points. 1, 2, 3, 4, 5, 6, 7. We're not going to need that many. Negative 1, 2, 3, 4, 5, 6, 7. We won't need that many. Up. 1, 2, 3, 4. We'll do 5, but we won't need that. Negative 1, 2, 3, 4, 5, 6, 7. We'll need some of those. Okay? Now, I want you to tell me some points to start graphing this. They didn't ask us to, but you tell me how to graph it. Where would you begin? 1, 2. So how would I do that one? Where do I find 1, 2? Right. 1, up 2. Just don't say yours. Okay, good. There we have it. All right. Now, the other point on here is 3, negative 6. So here's 1, 2, 3. And negative 6 will be 1, 2, 3, 4, 5, 6 down here. So it's going to be somewhere down there. Now, there's something useful for graphing that we haven't identified yet. I want you to identify it for me. Just based on what we know already, what's the other thing? I usually draw it as a dotted line. The what? Asymptote, the axis of symmetry. And what is the axis of symmetry? What one? x equal 1. It's always x equal 1. There is your axis of symmetry. Now, why did I bring that up at this point? You know it goes through the origin. Okay, that's how we do it. X equal 1, the vertex. Okay, x equal 1. In fact, you can take this thing and make it an equation. X equal 1. Okay. Now, but how is that advantageous for us now?
You can reflect the point from.
Say again?
You can reflect it from.
Yes, reflect that. And how far is that from the axis of symmetry? 2 units. So move 2 units over here. There you have another point without even working for it. Okay? Now, there's one other, and this isn't as easy to do in this form. This is about the only thing that's not easy in this form, but there is the one thing, and that's the y-intercept. Where is the y-intercept always?
0.
What 0? What is 0?
At 0, 0.
No, okay, 0, 0 is the origin. That may or may not be on this graph. You happen to be correct. I think that it is. But how do you find that? How do you find the y-intercept? What's always true about a y-intercept? Y-intercept is always on the y-axis, and what's always true about every point on the y-axis? One of its ordered pairs. X is equal to 0. So if you set x equals 0 down here, f of 0 is equal to what? Negative 2 times 0 minus 1 squared plus 2. That would be negative 2 times, what, 0 minus 1? Negative 1 squared plus 2. And what in the world is negative 1 squared? Negative 2 times 1 plus 2. And what's negative 2 times 1? Negative 2 plus 2? 0. So you're absolutely right. The y is 0 when x is 0. So you're right, it's at the origin. It's not always. Okay? Now, can we do anything else just based on that?
You can reflect it.
Say again?
You can reflect it.
Reflect it, and what will that give us?
1, 0.
No, there's 1, 0. 2, 0. 1 unit over. And you know what? I bet you that's all we can plot anyway. Okay? So here's your vertex. Here's your parabola. Goes up like this, reaches up there, comes down like that, and goes back down. There we have it. Now, they didn't have us draw it, but we drew it. Okay? And you see it looks fairly similar to one in the book. Theirs isn't quite as pretty as mine. Okay? Now, however, in the book, it says the function in standard form is f of x is equal to minus 2 times, and if you think I botched it, they botched it too. Did you notice that? They say x minus 2 squared plus 2 is x minus 1 plus 2. So that's an error in the book. You don't find many of them, but there's one. Okay? So if you make that correction. And like I said, there is a checkpoint well worth your time and effort to do the checkpoints. I'd say as soon as possible after you leave class. All right, any questions on this? Yes? Okay, say this a little louder. Okay. Yeah, if they, like this point here, yeah, there's no place really to plug it in until I've already erased it. You get it into this form and then plug the 3 in for x and the minus 6 in for y. And that's used to calculate the a, because there's nothing in what they give us here that tells us anything about a. Unless you really look at it carefully and see that the vertex being up here at 1, 2, and that point being down here at 3, negative 6, you know A has to be negative, okay? Because there's no way it's going to be opening up if your vertex is here and the point is down here. So that tells you that A is negative, but that's all it tells you. To get the value of it, you have to plug it. Now, is that what you were asking? Yeah. No. Oh, it wasn't? Was? Okay. This tells you plug in exactly here and here. The vertex is great information. It tells you exactly what to plug in for H and K in your standard form. And if they're looking for standard form, leave it in standard form. Don't go through and square things and do like that. If they're looking for standard form, there it is. Really easy to get. Pretty easy to get. Any questions? Good question. All right. Now, I think we're ready to go to the next page. Okay, let's see what else it says. Yeah, I think we already did that. Okay. Now we're going to talk about finding minimum and maximum values. Now, wait a minute. A minimum and maximum value for a quadratic equation, what is that always going to be? And we call that the vertex, or the vertex, the bottom of the parabola. Depending on which way it's opening, it's going to be one of those. So guess what? We've already found them. They're the vertex, okay? But guess what? There's an easier way to do it. And here's what we're going to do. Many applications involve finding maximum and minimum values of a quadratic function. Like, how high does the baseball go? That's something you're always interested in, right? Okay. By completing the square, we got to do that again? Yeah. By completing the square of the quadratic function, f of x equal ax squared plus bx plus c, you can rewrite the function in standard form. Now, that was sort of cheating on their part, wasn't it? Let's us do that. Here's f of x is equal to ax squared plus bx plus c. Now that's how they usually give you most of your functions, not in standard form. And what was our procedure for getting in standard form? Say again? Okay, we factor out the a from the first two terms. So a out of x squared will be x squared. But a factoring out is the same as dividing. So that's going to be plus b over a times x. Oh, and I forgot to do something, didn't I? Put in my blank. Yeah, you got to say it really nasty. Okay. Okay, plus c. Okay. Now, timeout, is that the same as this? It sure doesn't look the same. But what happens if we multiply through? A times x squared is ax squared. A times this thing, the a's go out, you get plus bx plus c. Yeah, that's the same thing. Okay. Now, what's the next step in completing the square? Anyone recall? Oh, it was a long time ago, at least a week, wasn't it? Or close to it anyway. How do we go about completing the square? Has to do with this number right here.
You square it and divide it by 2.
Not quite square it. You take half of it first, then square it. Okay, so let's take half of it, and that will be over 2. Let's multiply it by half. Square that, and that's going to be b squared over 4a squared, right? Now, remember what I also said? As soon as you take half of that, write it down. This will be x plus b over 2a squared. That's going to be the binomial whose perfect square is that trinomial. But what have you just done? You just changed the problem because you added this term. Well, you also took half of this, okay? But when you added this term, you didn't just add that, you added a times this. Well, the a times 1 over 4a squared, that will make it 4a. So this becomes, what you've added is a b squared over 4a, okay? So I'm going to do subtract a b squared over 4a. All right? And that gives us plus c minus b squared over 4a. Now, let's see if that's the same thing that they got over here. Okay, you got that firmly planted in your mind. Okay, see what they got? X times x, a times x plus b over 2a, yep, squared, plus c minus b squared over 4a. Whoops, wrong way. Plus c minus b squared over 4a. Yep, exactly the same. Now you've got it in standard form. Isn't that ugly? Okay? This is what we did before. What did we call this thing right here? H, only it was minus h, right? Because that needed to be a minus sign. So minus b squared over b over 2a. And over here, this whole thing we called our k. Now, I'm not about to remember that and call it k. I'm going to work it out and figure out what k is. But guess what? This h is pretty easy to do. That's minus b over 2a. Okay? Now, have we seen something like that before? Does that ring a bell somewhere? I want someone to recite to me the quadratic formula if you can. If you have, same thing we started with before. Let's go back to this one. If you had an equation, ax squared plus bx plus c equals 0. That's an equation. What is the solution for that? X equal, you want to remember how that goes? Minus b plus or minus the square root of b squared minus 4ac all over 2a. Look at this thing right here. Minus b over 2a. And then you do plus or minus of that. So basically, that's your vertex. That's where you start your x, and then you do plus or minus on either side of that, drawing your graph. So that is your h, minus b over 2a. Okay? Same as we saw here, that's it. So your h is equal to minus b over 2a, and your k is that thing. And who cares? I'm not going to remember that. That's too many squares and minus that. Yeah, I'm not. But minus b over 2a, I can remember that. Okay? Now, so the vertex of the graph is, and here's how they say it, minus b over 2a. That was easy. And then the y? F of minus b over 2a, right? Y is equal to f of x. If that's your x, this is your y. So all you do is plug that in to your function. Far easier than trying to remember c minus okay? That gets me confused. Okay? So, we found another way to find the vertex, but this is also a way to find the minimum maximum, because that's always the vertex, okay? Consider the function f of x equals ax squared plus bx plus c. The vertex is going to be minus b over 2a, and then plug that in here and figure out what your k is, okay? Now, when a is greater than 0, meaning that's a positive a, then this is going to be a what? The vertex will be your minimum. And when a is negative, the vertex is going to be your maximum, okay? So f has a maximum value at x equal this, and that maximum value is your k, alpha minus b over 2a. And when a is less than 0, in other words, a negative number, alpha is then a maximum, and it will be again at x equal minus b over 2a, and the maximum value is alpha minus b over 2a. Now, do you always have to remember the b over 2a? No, it's just pick out what your number is and go for it. So let's see, this is top of There it is. Okay, I was trying to find out what page I was on. Okay. So we're ready for an example. Okay? Top of page 119. The example's next. I told you we were interested in the path of a baseball. Path of a baseball after being hit, okay, is given by the function f of x is equal to minus 0.0032 x squared plus x plus 3, where f of x is the height of the ball, baseball, in feet, and x is the horizontal distance from home plate, also in feet. Okay? The question is, what's the maximum height of the baseball? Okay. Now first, what kind of function is this? It's a quadratic function. Is that one you particularly want to factor? No. Okay, nowhere close. But we don't need to anyway. Okay? F of x is the height, x is the distance from home plate. So let's just see if this is making any sense whatsoever. If you're at home plate, what's your x? What value? 0. And what would this tell you the height would be? If x is 0, that's 0, that's 0, what's the height? 3 feet. Isn't that where you want to smack that off? Okay, right about waist high. Yeah, that's going to be pretty good. So let's see how high it goes. What will that be? This is, you told me, a quadratic function. What will its graph look like? A parabola. And will it be opening up or down? Why? A is negative. Well, good. I want my baseball to do like that. I don't want it to dig into the ground and come back up. No, we don't want that. So we want it to go up in the air and hopefully go over the fence. Okay? We aren't interested in the fence right now, but let's see what the maximum height will be. That's going to be your maximum y value. But where is that going to occur? At the vertex. And what is the value of the vertex? Now, do y'all want to complete the square on that one? I don't, okay? So much easier than that is tell me where the vertex is. What is your h? Oh, I thought we just went over that till it was obnoxious. Say again? Minus b over 2a. Now, we got to figure out what the a and the b are here. What's your a? Negative 0.0032. And what's your b? 1. So that's not going to be too hard to do. It's going to be minus a 1 over 2 times negative 0.0032. Right? Okay. Now, I'm going to look at this and say I've got a minus here and a minus there. That's going to become a plus. Is that all right? I want that vertex to be up there somewhere. So that feels pretty good. So this is the same as 1 over 0.0064. So pull out your handy-dandy calculators and see what 1 over 0.0064 is. Bless you. Again. Say again. 1 over 0.0064.
I got 156.25.
156.25 feet. Now, what is x telling you or h telling you? How far you are from home plate. That doesn't tell you the height of the baseball. That's what we're looking for. But guess what the height of the baseball is? That's going to be your k, so you plug this into this. So we're looking for f of 156.25. That will be minus 0.0032 times 156.25 squared plus 156.25 plus 3. Keep your calculators out, folks. I don't want to do that by hand. Okay? Now, with a calculator, you probably can just plug it in as you go, okay? But if you don't want to, you don't have to. You can do that first if you want to. Then you can multiply it by that. Then you can add that and add that. However you do it on your calculator, do it. Tell me what you get.
What are we trying to find? Not plugging it in.
That gives you the maximum height. Because this tells you the H value, in other words, how far you are from home plate when you reach that vertex. The maximum height will be the Y value when you're there. Okay? And that will be the K. Okay? Anyone got a calculator? Punching away. 81? 81.125, and again, that will be in feet. And let's see how the book did. Look at that. They got it right. Good for them. Okay. Any questions? All right. Now, do you like finding your H this way, or would you rather complete the square? Sort of crazy answer question, isn't it? This is far easier. So, you might say, I never have to complete the square again. Don't bank on it. You said that when you did the quadratic formula too. But we've had to do it over and over. It's a very common practice, but anytime you can get out of it, it's not bad. Okay. Can I go and erase this? Are y'all still writing? It's going to show up in what they do also, but theirs may not be as pretty as mine. Okay? Everybody got it? Can I erase? Okay. All right. For this quadratic function, you have f of x is equal to ax squared plus bx plus c, okay, where the a, which is negative 0.0032 x squared plus x plus 3. So your a is negative 0.0032 and the b is 1. Do we even care what c is?
No.
Not for what we're doing now. And we sure aren't going to use it to figure out your k by that other formula. It's far easier to, or more direct to do it this way. Okay? So you know your a and your b, you can write down what your h is. H is equal to, or x, they say, is equal to negative b over 2a. So that's the distance from home plate. So let's plug that in like we did. And that gave you 156.25 feet from home plate. That's how far it is when it's reached the maximum height. So now we just have to plug that in the formula, f of 156.25. Please use your calculators, and that gives you that which is 81.125 feet. I would round that to 81 feet. I mean, who cares about 0.125 feet? But anyway. Okay. Any questions? All right. I think that's the last slide of the section. Okay? There is vocabulary, top of page 120. Let's hit that. Linear, constant, and squaring functions are example of blank. Say again?
Parent.
I can't hear you.
Parent function.
They are parent functions. You're absolutely right. There is another, like the first name of this chapter. I mean, yeah, polynomial functions. They're also examples of polynomial functions. Okay? Number 2, a polynomial function of x with degree n has the form of f of x equal a sub n, x raised to the nth power, plus a sub n minus 1 times x raised to the nth minus 1 power, plus dot, 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 plus, then you get a, I'm going to put in an extra one, a sub 2, x squared plus a sub 1, x plus a sub 0. As long as that a sub n is not equal to 0, that leading coefficient is not equal to 0, where n is a blank blank, n is a blank positive what? not just number, for there to be a polynomial. Integer, a positive integer, and the a sub n's, a sub n minus 1, and all your little a sub minus, a sub 2's, a sub 1, a sub 0 are blank numbers. If they got any restrictions. Not imaginary. Real numbers. Okay, they are real numbers. The n's are only integers, in fact, positive integers, but the a's can be any real number in the world. Positive, negative, fraction, decimal, rational, or irrational. Can't be for the n. N is only positive integers. Number 3, a blank function is a second degree polynomial function, and its graph is called the blank. So what? A blank function is a second degree polynomial. Say again? Quadratic, and its graph is called a parabola. Okay, number 4. When the graph of a quadratic function opens downward, its leading coefficient is negative, and the vertex of the graph is a... The graph is a parabola. The vertex is a maximum. Perfect. Okay, very good. Homework exercises. I would do all 4 of 5 through 8. Now, only 5 and 7 will have answers in the back of the book, and will be at calcchat.com, but you should be able to match all 4 of those really easily. Okay? Then do either 9 or 11. They're both at CalcChat. 9's at CalcView. Do any of the odds, 13 to 25. They're all at CalcChat. 17's at CalcView. And it says using technology, but I don't think you'll need to. I think you can do this on your own. Any of the odds, 27 to 33, they're all at CalcChat. 35's at CalcChat. Any of the odds, 37 to 45, these are a lot like the ones we just did today. That first one we did. Those are all at CalcChat. 37's at CalcView. 47 and 49 are both at CalcChat. Okay. 51 through 55 are all at CalcChat. The odds 57 to 61 are at CalcChat. 57's at CalcView. There's some number problems, and for some reason math book writers love these number problems. 63 and or 65. And then here's a diver. That's number 67. That would be pretty, it's sort of like the height of a baseball, only different. And then there's a 69. That's more of a economics type problem. So if that's more interest to you. 71 is maybe business owner, maximum revenue, or economics, either one. That would be 71. Maximum area. Here you have a cattle rancher putting up fences. So if you're ever going to do that, 73 would be a pretty good problem. There's a couple true, or one true false, 75. They're all at CalcChat, by the way. And then you can think about doing 77 if you want to. That should be at CalcChat as well. Verifying a vertex is at CalcChat. And 81's a proof. It should be at CalcChat as well. And there's a little project on height of a basketball. You don't realize it now. There's one situation in which shooting a basketball doesn't really apply to what we've been talking about here. But any free throw, any jump shot, always going to be following a parabolic arc. The one that doesn't is what? I'm guessing right now, I don't know this for sure, but Josh might be the only one in the room that might do this shot. Doesn't follow a parabolic arc. Anybody? I can't pretend to do it. A dunk! Yeah, that doesn't follow. That's just a straight down, okay? So all the rest of your basketball shots are parabolas, okay? Okay, you ever? Yeah, I thought so. Okay. So, that might be a good project for you. I don't know. That's up to you. So let's move on to 2.2. All right. I didn't mean to. James, you dunk too? Okay, I don't either. Okay. All right. Nowhere close for me. All right. Where is my... There it is. Okay. 2.2. And I guess that maybe you could claim when he does the big windmill here, that may be close to a parabola, but probably not. Okay. You don't do that, do you? Never mind. All right. 2.2 is not coming up here. Why isn't it coming up? Maybe it's down here. No, it isn't. Well, I want 2.2 open. There it is. Okay. And we'll get the slideshow from the current slide and go from there. All right. We already had the gal at the swimming pool, so what are we going to hit this time? Polynomial and rational functions. We're still on the polynomial part. Now we're going to be doing polynomial functions of higher degree. Section 2.1 was mostly quadratics, degree 2. Now we're going to do higher degrees. Okay? Objectives here are to use transformations, we love them, don't we, to sketch the graphs of polynomial functions. We'll use, now they call it a leading coefficient test to determine the end behavior of graphs of polynomial functions. I like to call it the leading term test. I think that includes more than just the coefficient. And we'll find and use the real zeros of polynomial functions for sketching aids. Okay? Well, finally, we'll use intermediate value theorem to help locate the zeros, the real zeros of polynomial functions. Okay. So let's start, as you would expect, graphs of polynomial functions. Okay? In this section, we will study the basic features of the graphs of polynomial functions. The first feature is that the graph of a polynomial function is always continuous. What that means, there's no breaks, there's no gaps, there's no holes, they're continuous. Okay? This graph is continuous. Don't see any holes, any breaks, any discontinuities. Okay? Essentially, this means the graph of a polynomial function has no breaks, no holes, and no gaps. Okay? All right. So that's could be a polynomial function. Okay? Continuous. There's one, and here's one that's not. This graph in this figure is not. It may be a piecewise defined function, and each of these pieces may be polynomials, but this is not a polynomial. This is piecewise, because you can tell there is a gap there, a break, where it's discontinuous. That can't be, the whole thing cannot be a polynomial function. This part here could be, that part there could be, okay? But with the break there, it's not a continuous function. It is not a polynomial. It's piecewise, okay? Now, the second feature, not only is it continuous, but it's also smooth. Okay, now what does that mean? Any of the changes of directions are smooth changes. You don't have any peaks or points. You don't have any cusps or corners. You only have smooth, rounded changes. This one's pretty sharp, but it's still rounded. It's not pointed like an absolute value function. Okay? This is rounded, that's rounded. Even that one's rounded. So that means it's smooth. Rounded turns as shown here. So two things about polynomial functions, the graphs, smooth and continuous. I like to say smooth like jazz, but y'all may not like jazz, but anyway. All right. Polynomial function cannot have a sharp turn. Absolute value function is not a polynomial function. That has a very sharp pointed turn. Can't happen. So absolute value of x, not a polynomial. Okay? Now, they say this, but don't take it too much to heart. The graphs of polynomial functions of degree greater than 2. That quadratic function is really easy. 1 max or 1 min. And it all depends on the sign of a. Okay? So that's pretty easy to do. And you can tell exactly what point that is by minus b over 2a. Okay? That gives you the h value. plug that in, you get the y value, the k value, okay? But when you have degree greater than 2, they're more difficult to analyze than the graphs of polynomials of degree 0, 1, and 2. Those are pretty easy. However, they're still not hard to do, okay? And we're going to break it down into pieces, and I want to make sure I don't run out of time here. However, using the features presented in this section, coupled with your knowledge of point plotting, intercepts, symmetry, you should be able to make reasonably accurate sketches by hand, okay? And the polynomial functions that have the simplest graphs are the monomial functions like this. F of x is equal to x raised to some power. We often call those the power functions because they don't have anything else to do with it. N is an integer greater than 0. N positive integer. Remember, just like before. So that is the easiest to do. And you've seen these before. These were our parent functions, that we talked about before. Now, here's a feature that we may have pointed out before, but we're going to focus on it here. When n is even, the graph is similar to the graph of a parabola. Here is the graph of the parabola, y is equal to x squared. When you have y is equal to x to the fourth, notice the thing. They still intersect at 0, 0, and they cross at -1, 1, and 1, 1. Every one of these does. So those 3 points are in common. Now what's different when you go up to x equal 4, your outside plus or minus 1 is sharper, more upright. Inside, it's sharper coming down, flatter near 0. And when you get x equals 6, it'll be sharper here, flatter here, sharper there, okay? X equals 8, it continues the process. But they all basically look like that. So when you have even powers, they look like sort of like your parabola. When you have an odd power, now if it's equal to 1, that's just going to be y is equal to x, okay? It's going to start negative, go to 0, and go positive, okay? Well, all these do. But they look more like your cubic function. Comes up, curves in near 0, and then goes up. Again, they go through, this time, -1, -1, 0, 0, and 1, 1. All of them go through those 3 points. And those are odd powers, okay? The difference is, the larger the number, the steeper it is near 1 and -1, okay? And the flatter it is near 0. But other than that, they have the same characteristics, okay? When they're even, they come down and touch the x-axis and go back up. When they're odd, they cross the x-axis and go back up. They hang around longer, the larger the power is, but they still do like that. So those are a couple features to keep in mind, okay? Those are your power functions, okay? Moreover, the greater the value of n, the flatter it is near the origin, and the steeper it is outside that flat part, okay? So let's sketch the graph of each of these functions, okay? Let me get my pen set up, okay? Let's do the first one. F of x is equal to minus x to the fifth. Let me tick off a few points here. 1, 2, 3, 4, 5, 6, 7, 8. Negative 1, 2, 3, 4, 5, 6, 7. Positive 1, 2, 3, 4, 5, 6. Negative 1, 2, 3, 4, 5, 6. Okay. Whatever. Give me some points for f of x, the A one. Do you want to keep that in black? Okay. Give me a point. 0, 0. Perfect. Give me another point. Second? 1 what?
2.
Second?
1, 0.
Really? When you plug 1 in for x, you get 0 for y. When you plug 1 in for x, you get negative 1 for y. Okay? So 1, negative 1 will be on that. Okay? Give me another x. 2. Ooh, okay. And what do you get when you plug in a 2 for x? Negative 32. I think that's off scale. Okay? Way off scale. Okay, but you get the idea. It's heading downhill, right? Give me another x. Negative 1. What do you get? Positive 1. Okay? And then if you did negative 2, you'd be going to positive 32. So basically this is coming down really steeply here, hanging around your 0 for quite a while, and then going real sharp downhill again. There is your graph of f of x equals negative x to the 5th. Just like the one we saw earlier, there was x to the 5th here, except it's reflected across the x-axis. So mine is a bit more crunched in this way. They spread theirs out. Okay, let's do the B one. What color you want B to be? Pick a color. Second? Orange? Okay, orange, you good. Okay. Now, what can you tell me about that H?
Negative.
Okay, it's negative. Why do you say negative? What do you mean by that? You may be right, I just don't know what you mean by it.
Because isn't it whatever is on parentheses for H, the number would be the difference?
Okay, so the X is moving to the left negative by 1 unit. So the origin goes over to here, right? There's your orange. Okay, now what does it do from there? Okay, remember this is a lot like this one. Okay, there's your origin, except it's moved over here, so all that will move over 1 unit to the left. So the 1, 1 will move over and become 0, 1. The minus 1, 1 will be minus 2, 1. Okay, let's see if that works. Okay, you're moving everything to the left 1, so that would be minus 2, 1 and 0, 1. Now, mine's not very symmetric, is it? Okay, sorry about that. But see, if you plug in a 0 here, you get 1, right? 0 plus 1 is 1. 1 raised to the 4th is 1. If you plug in a minus 2 here, you get minus 2 plus 1 is minus 1. Minus 1 to the 4th is 1. Okay? And from there, again, mine's not very, it's very steep here, very flat here, and very steep again here. Something like that. There is the graph of your H. Okay? Now, any questions before I erase this? Okay, remember we use all the tools we had before about negating, reflecting, shifting, stretching, whatever, shrinking. All right, so let's erase this and see how they did theirs. Because the degree of this is odd, that means the graph is going to go in opposite directions. But because of the minus sign, it isn't negative when it's negative. It's positive when x is negative and negative when x is positive. Okay, so that minus sign flips it around. The graph is similar to the graph of y is equal to x cubed, only different. Okay, no, okay. And in this figure, note that the negative coefficient has the effect of reflecting the graph in the x-axis, or across the x-axis. So that's pretty much how ours looks, right? Say yes. Okay, good. All right. Now, the B part, that graph has as you pointed out, a horizontal shift to the left 1, okay? But then it looked a lot like a parabola, only flatter down here, steeper out here, and it went through 1 to the left of this minus 1, that would be minus 2, 1,
1 to the right of minus 1 would be 0, 1. Okay, so everything got shifted to the left once, and flatter down here, steeper here, there it is. Make sense? They just didn't use orange. Sorry about that. Someone's into Halloween, I think. Okay, all right.
Any questions on that? That was example 1. There is a checkpoint. I would definitely do those checkpoints. There's 4 of those. So take a look at those. If you have any problems with them, remember, LarsonPrecalculus.com is right there for your assistance. Okay? So let's move to what they call the leading coefficient test. I call it the leading term test. And here's why.
Well, we'll get to it. Okay? In example 1, note that both graphs eventually either rise or fall without bounds as x moves to the left or right.
Let's go back and see what they're talking about. Okay, see this one?
As x gets larger and larger, negative or positive, this is really going uphill fast.
Okay? The previous one?
As x gets very large negative, this goes very large positive, as x gets very large positive, that goes very large negative.
Very, very rapidly. I mean, really fast. Okay? Let's go back and look at these.
Notice going up, down, going up.
So, in the long run, your polynomial functions are going to be going to infinity. Every one of them. Okay? For larger and larger x is either positive or negative, your polynomials are going to be going to either positive or negative infinity. Okay? And that's all governed by that leading term.
Okay? Whether the graph of a polynomial function eventually rises or falls can be determined by the function's degree, even or odd, and the leading coefficient, positive or negative. Okay? And that is indicated, and why do they call it leading coefficient test? That would give you this part, but the leading term gives you this part and that part. So why don't they call it the leading term test? I don't know. But I call it leading term test.
Because that incorporates both the degree and the sign of the coefficient. Okay. So here's the leading coefficient test. Whoa.
Okay. As x moves without bound to the left or to the right, the graph of the polynomial function, f of x equal all this mess, okay? All it depends on is that first term. If you get large enough x value here or here, this is going to dominate. It doesn't matter whether you got a plus a or minus a down there. In the long run, this is going to dominate. It even wipes out that one, or even the x to the n minus 1. The leading term takes over, eventually, if you get large enough x's. So when n is odd, okay, when that leading coefficient is odd, that's going to act like your cubic function, 5th function, 7th function, because those are the odd ones, okay? So and when n is odd, and that leading coefficient is positive, then as x gets large positively, so will your function. As x gets large negative, so will the function. Okay? That is leading coefficient positive. Now, if you flip it and make the leading coefficient negative, then that flips the whole thing, and as x gets very large negatively, this gets very large positively. As x gets very large positive, the function goes very large negative. Now notice how they express this. As x goes to negative infinity, f is going to some infinity. As x goes to positive infinity, f is going to some infinity. In every case here, all 4 blanks are infinities. One x is going to be negative, 1x positive. 1x negative, 1x positive. That's the x's, okay? Now, the other, what does the f do? That's the only thing you have to figure out. You know it's going to an infinity, whether it's going to be plus or minus. That's all you have to do. So when you see these on a quiz, you can fill in, there's going to be 4 blanks there. As x goes blank, f of x goes blank. As x goes blank, f of x goes blank. When you see those, put an infinity in every blank. And for the two x's, put one positive and one negative. Then all you have to figure out is what sign to put with the other one. Okay? It's that easy. Okay. Now, let's go to even ends. When you have an even end, that means you're either on the up and up or down and down. They go in the same direction because, and notice how they do, as x goes to negative infinity, this one goes to positive when the a sub n is positive. As x goes to positive infinity, f of x is going to positive infinity again because it's on the up and up when a is positive. When a is negative though, then when x goes to negative infinity, so does your f, and when x goes to positive infinity, f is still going negative. Because if you've got an even end, they're going in the same direction. Odd ends go in opposite direction. Okay? Even end goes in the same direction. Feel like I'm doing semaphore up here, right? Never mind. Okay. Now, does that make sense? Okay? And then, again, when you have the four blanks there, put an infinity in every blank. And one x put a negative infinity, the other x put a positive infinity. Okay? Then figure out what signs go with your two f's. Okay? That's all you have to do. Okay? Now, what happens in here? That's all those other terms. The n minus 1, n minus 2, n minus 3, x squared, yeah. Those are those terms. That determines this. The leading term, that leading coefficient, that leading exponent, that determines which way it's going in the long run. Okay. I think we just have done page 125. We're ready for example 2. So that's where we'll begin next time, if I can find my pencil, example 2. And let's see if we got enough done for you to do some homework exercises. Okay? Let me get my page marked here. We didn't get very far, but we got a little ways. I think you can do you might be able to do 9 through 14. If you can't, don't sweat it. When we do the first few examples, then you'll be able to do that. Okay, but you got plenty to do from 2.1, right? All right. Now notice we're moving a lot faster in this chapter than we did in the other one. And that will hopefully continue. When we finish 2.3, it'll be time for the next quiz. Okay? So that might even be, well, we're going to miss, well, no, it might even be the end of next week. We'll see. Okay. Any questions? All right. Good deal. We'll see you on Thursday.